To this session. The title of my work is a family of parabolic type flat surface. This work is developed joined with Alexander Arredondo and Israel Morales. Okay, let me start with our main result. Okay, second. Oh, what's up? Okay, I got it. Given an increasing sequence of positive real numbers, show that its series associated to this sequence diverge, then such sequence defines a torsion-free and of first-kind Fuchsian group gamma x, so that the following condition hold. The first one, the quotient space is x given by the hyperbolic plane by the Fuchsian group gamma is a complete surface of parabolic type. The second one, the Riemann surface Sx is isometric to a zero twist type flat surface. Okay, to understand this theorem, we are going to treat 2 over the n space of non-compact surface and introduce some example of non-compact surface so that the Lossner's monster, the flat surface, then introduce the type problem and introduce the geodesic pair of band and Fenchel-Nielsen parameters. Then we're talking about the type flat surface and get some geometric ideas of our proof. If the time is good, we introduce a nice construction of Fuchsian group uniformization to the Lossner's monster. Okay, there we go. Geometrically, one end on a surface is a point to at infinity, or equivalent, the ends are the different way to run away from a compact set. In the picture, you can see a surface having exactly 4 ends. Okay, you can go to the infinity in this way, or this way, or this way, or this way. Ready? So when you go to the infinity, you can find always half. When you go to the infinity in this way, you can hold or handlets. Okay, you go, found handlet, go, found handlet, and so on. So under this idea, a surface have associated a triplet. This triplet is determined by the genius of the surface, the set conformed by the ends of the surface and the ends having infinity genius. Okay, these ends having infinity genius are also called a no-planar end. Okay, we can give a topology for the set of ends of an surface. When you give a topology, this topology is a Hausdorff space, is totally disconnected and is compact. Moreover, the set of the surface having an infinity genius is a closest subset of the n space of the surface. Okay, this triplet is the invariant topological in each surface. Okay, we are prepared to introduce the classification theory of non-compact surface. So if we have two surfaces, S1 and S2 having the same genius, these guys are topological equivalent if and only if there exists a homeomorphism S from the n space of the first one surface to the n space of the second surface, so that when you take the image of the ends having infinity genius of S1 under F is equal to the n space having infinity genius of the second one surface. This is the classification theorem of non-compact surface. Okay. Having this theorem, we introduce some basic example of non-compact surface. The first one is the Lossner's monster, that is the surface having infinity genius and exactly one hand. You can think this surface has a complex plane attaching infinity many handlets, right? This guy, in this picture, you can see the Lossner's monster. The second one example are the flat surface. The flat surfaces are the surface having genius 0 and n space homeomorphic to the ordinal number omega plus 1. In the picture, you can see a flute surface, okay? This guy can be think like the complex plane, removing the complex plane, removing the positive integral. Okay, this surface is homeomorphic to the float surface. Okay. Now I'm going to introduce you or talking about the type problem. Ouch, sorry. Okay, the type problem consists in the classification of open Riemann surface from the uniformization theorem and the existence of Green's function of Riemann surface. So, by the uniformization theorem, there are only two types of simple connexes open Riemann surface. This type open Riemann surface I represented by the Poincaré unit dig and the complex plane. So, if we have a simply connected open Riemann surface, so that is conformally equivalent to the complex plane, then the surface is called parabolic type. So, if the simply connected open Riemann surface is conformally equivalent to the Poincaré unit dig, then the surface is called hyperbolic type or hyperbolic. So, in 1930, the question of the existence of a green function on open Riemann sources was inserted in terms of several mathematics like Alfors, De Valina, Sario, among others. In this way appeared the following definition, so that classifies the open Riemann surface. This is the following definition given by Otsuka Makoto. An open Riemann surface is parabolic type or parabolic if S does not carry a negative non-constant subharmonic function. All open surfaces which are not parabolic will be called hyperbolic. Having the definition, we try to tell when an open Riemann surface is parabolic or hyperbolic type. This is the problem. This is the problem, the type problem, right? Okay, I can give some equivalent statement of when a surface is a parabolic type. An open Riemann surface is parabolic if only if one of the following conditions is valid. The maximum principle is valid on the Riemann surface, or the harmonic measure of the ideal boundary is vanished. Ideal boundary is the same as the n space. 3, there is no green function. This is the basic equivalent statement of a parabolic type in Riemann surface. So there are other equivalents from point of view of geometry, dynamical system, and so on. I'm going to explain you about that. Okay, this is the dig theory. Okay, if the open Riemann surface S is the quotient of the hyperbolic plane by a Fuchsian group gamma, then S is parabolic if only if one of the following conditions holds. 1, the geodesic flow on the unique tangent bundle of S is ergodic, or the Poincaré series of gamma diverge, or the group gamma has the Bowen's property, or Mostow rigidity holds for gamma. In a recent work, titled The Type Problem of Riemann Surface via Fenchel-Nielsen Parameters by Basmajian, Hakobyan, and Šaric, they describe sufficient conditions on the Fenchel-Nielsen parameters of a surface to ensure that such surface be parabolic type. So in this way, I'm going to describe the definition of the Fenchel-Nielsen parameter in a Riemann surface. So first one, I need to introduce the definition of geodesic pair of bands. It's a easy definition. A pyropan is a surface homeomorphic to a 2-sphere minus 3 disk. Okay? A geodesic pyropan is a pyropan equipped with hyperbolic metric so that its 3 boundaries curve are geodesic or curved. In the first one picture, in the left, you can see a geodesic pyropan having exactly 3 geodesics in this boundary. Okay? In the middle, have a geodesic pyropan having 2 geodesics in the boundary on only 1 punched or cubes, right? And the last one, in the right, we have a geodesic pyropan having 1 geodesic in this boundary and 2 cups or punched in the boundary, right? So now, when we have a 2 pyropan, we can using isometry to glue in both pyrospans. So imagine we have a 2 geodesic pyrospan, okay? And each one of them have a geodesic in this boundary. In this case, look, I have the two piece. Imagine that this guy had a geodesic pyrospan. This guy is a geodesic in this boundary, and this guy is a geodesic in this boundary. Both geodesics have the same length. So using an isometry, we glue and put together to, both geodesic pyropan. Okay? So, but in this way, we can glue both in this way, or this way, or this way, or this way, infinity way. Okay? So, this way, okay, we can associate a pair to the H gluing. This pair is determined by 2 real numbers. The first one real numbers is called the length parameter. The length parameter is the hyperbolic length of the boundary of the geodesic using to the gluing both geodesic pyropans. The second real number is called the twist parameter. This is a real number in the closed open interval with endpoints, -1/2 and 1/2. So this number determines this position in both geodesic pyropan. Okay, so I will not go into the precise description because it's not necessary in this talk, but it's necessary you have the idea in your mind. What does that mean? This a pair when you glue to geodesic pyropan, right? Okay. Now I'm ready to define a type flat. Okay, no, Fenchel-Nielsen parameter. Okay. If you have a hyperbolic surface obtained by gluing contact many geodesic pyropans, in this case, the family is Pn with n in the positive integer number in the way described in the slide before. So the choice in the gluing are given by pairs, okay? Length parameter and twist parameter, right? So when you put together all these pairs, you define a collation of these pairs or length and twist parameter. This collection is called the Fenchel-Nielsen parameter, okay? And this family is associated to a hyperbolic surface obtained by gluing contact many geodesic pyropan, okay? This is the Fenchel-Nielsen parameter. Now I'm going to introduce the definition of type flat surface. Okay, a type flat surface is a hyperbolic surface obtained by starting with a geodesic pyropan P0. I have my geodesic pyropan P0. This guy have exactly 2 punched now, consecutively gluing a geodesic pyropan P1. This P1 had only 1 punched and put together using the geodesic boundary. Now, put together to the geodesic pans P1 or the geodesic pans having only 1 puncture, and so on. I glue in this geodesic span like an infinity chain, right? You can see a picture or of a type flat surface coming from this identification using geodesic span, right? So obviously, when you glue in this geodesic span, the type flat surface has associated is Fenchel-Nielsen parameter, okay? Using the type flat surface and the Fenchel-Nielsen parameters, we are ready to introduce a theory to guarantee when a type flat surface is of parabolic type. But this type flat surface is a kind of special surface for our study. Okay, let me talking about the theory. The theorem is studied in the same way. Let X be a zero twist type flat surface. It means that when you use the Fenchel-Nielsen for determine the type flat surface, all the twist parameters are zero. Okay, it means zero twist parameter is mean that the twist parameters is always zero. Okay, then the surface is parabolic type if only if one of the following conditions holds. The first one, the surface S is complete with respect to the hyperbolic metric, or the series defined by the Euler number raised to the power negative length parameter middle diverge. Okay, so we need to use this theorem to prove our main result. Now, and again, I'm going to introduce or show and again our main result. Given an increasing sequence of positive real numbers, shows that if Z is associated diverge, then such sequence X defines a torsion-free and of first kind Fuchsian group gamma X shows that the following condition holds. First one, the quotient space is X given by the hyperbolic plane by the Fuchsian group gamma is a complete surface of parabolic type. Second one, the Riemann surface Sx is isometric to the zero twist type flat surface. Now, I'm going to introduce some geometric ideas of the proof of this theorem. Okay, imagine that we have a zero twist type flat surface. Okay, it's coming from to glue in a geodesic pair of span. Over here, there are our first one geodesic pair of span, gluing with the geodesic pair of span P1, using the geodesic gamma 1. There are the geodesic pair of span P2, gluing with the geodesic pair of span P1, using the geodesic gamma 2, and so on. Now, this type flat surface have n spans, remember, the ordinal number omega plus 1. Now, we're gonna, it's just label all punched in this surface, okay? We're gonna label the first function like a 0. This corresponds to the one puncture in the geodesic pair span P0, okay? The other puncture is labeled like a capital little S0, right? Now, we're going to the geodesic pair span P0, and we label its punched like a S1. We're going to geodesic span Pn and label its punched like is N, and so on. Okay? Now, I'm gonna draw on the surface a special geodesic. The first one special geodesic is called gamma 0. Gamma 0 is an infinity geodesic having endpoints, the punched 0 and punched is 0. Okay? Now I'm gonna draw the special geodesic gamma 0 having endpoint, the punched is 0 and S1. So this geodesic is special because when pass around through to the geodesic gamma alpha 1, this guy is orthogonal, right? Both are orthogonal. This is a property of this surface, of a zero-type flat surface, okay? These facts always happen in this surface, okay? Now I'm gonna draw other special geodesic. This geodesic is gamma 2, having ends point, the punched S1 and S2. And again, this guy is special because draw gamma 2, alpha 2 orthogonal. Both are orthogonal. Okay, and so on. We draw the other special geodesic with these properties, right? Now, we're gonna take our hyperbolic scissors, okay? I'm gonna cut around this geodesic, okay? We cut. So in this way, we turn the surface S into an ideal hyperbolic polygon P with infinity many sides. Okay, this polygon you can think like this way, or this way. Okay, let me explain you about this ideal hyperbolic polygon. Okay, its size comes from the geodesic gamma n. A geodesic gamma n define two sides in this polygon. These sides are gamma n plus and gamma n negative. Okay, and these guys are identified using a Mobius map. Okay, in this way, gamma 0 and gamma 0 plus, gamma 0 negative are identified using a Mobius map called G0. Okay, gamma 1 negative, gamma 1 positive are identified using a Mobius map called gamma 1. The half circle gamma n negative and gamma n plus are identified using a Mobius map Gn. So this sides in this polygon are special because they have the same radius. Okay, they have the same radius. Okay, now we're talking about the vertices of the polygon. The vertices coming from of the puncture of the type flat surface. It means the punched cal 0, you can put over the 0 of the real or the real axis. Both is the same. Okay, so when you take the puncture S, this guy define two vertices of the polygon. These vertices are Sn and negative Fn. Okay, and you put over the real axis. So, but these guys are nice because they are symmetric with respect to their imaginary axis. Are symmetrics. Okay, so in this way, you can define an increasing sequence of real positive number x, okay, so that Sn, the point Sn is equal to sum from 0, sorry, to n of x, y, okay? In this way, you define this point over the real line. So you want that the type float surface be complete. So in this case, you need the condition that you series diverge, okay? You need the series diverge. Okay, using this idea, you can get, and again, you zero twist type float surface. What you need to do? So you need to take the group gamma x generated by the set of the Mobius transformation Gn. Remember that this Gn identify the half circle in the boundary of your polygon P, okay? And you prove that this guy is a Fuchsian group, is a torsion free and first kind, and moreover, the quotient space is a complete float, is a complete surface of parabolic type, and moreover, this guy is isometric to a zero twist type float surface. Okay, these are the ideas of the proof of our main result. Now, I'm going to introduce a construction to get Fuchsian group uniformizing to the Lochness monster. Okay. Okay. Oh, first one, sorry. I need to introduce this theorem. Okay. From the theorem, we know that each increasing sequence of positive real numbers show that its series diverge, define a zero twist type float surface is x of parabolic type. Now, we can consider the space conformed by all sequence from the positive integer joined to 0 to the 5-dimensional real space endowed with the compact open topology. In this space, we consider the subspace M conformed by all increasing sequence of positive numbers so that its series diverge. Then, each point in M define a torsion-free and of first-king Fuchsian group gamma x such that the following condition hold. The quotient space is x given by the hyperbolic plane by the Fuchsian group gamma x is a complete surface of parabolic type. The Riemann surface is x is isometric to a zero twist type float surface. This theorem means that the space M is a modular space of our construction in the proof of the main result. Okay, it means this theorem. The space M is a modular space of our construction in the proof of the theorem. Okay. Right now, I'm going to introduce a Bowen to the Fuchsian group uniformizing the Lochness monster. Okay, we're gonna start with a polygon. Okay, this is a special hyperbolic polygon. Okay, we wanna take a hyperbolic plane and half circle with center over the even integers numbers and radius 1. Okay, you can see this polygon in the picture. The polygon is this guy. Now we're gonna draw 9 vertical strips. Okay, each strip having exactly 4 of this half circle. Okay, the first one strip is this guy. This strip is scale is 0. In the right, we draw the following strip, having exactly 4 half circles. There's 1. In the left, we draw the following strip, having exactly 4 half circle. Is -1. Okay, and so on. Okay. Look, the first one strip. Okay, in the first one strip, there are 4 half circles having color red and blue. Okay, the red one can be identified using a Mobius map F0. Okay, and the blue one can be identified using a Mobius map G0, right? From the topological point of view, if you remove the strip and gluing using this identification, you have a torus minus a disc, right? Only in this strip. If you develop this construction in H1 of this strip, in H1 strip, you have a torus minus a disc. So you can put together all these torus minus a disc, and when you put together, you obtain a Lochness monster like this one. Okay, what is the only one end of this surface? The only one end is the vertex of the polygon. When you put together all these torus minus a disc, these vertex are identified. Define the only one ends of the surface. And the surface has infinity genus because H1 strips define a torus minus a disc. Okay, this is a geometric proof, or is a geometric construction of a Lochness monster using a hyperbolic polygon with infinity many sides. Okay, I'm going to talking about the mathematics. So now you can define the Mobius map. This Mobius map identify the half circle described in the slide before. This guy is given by this formula. By this formula, so you can define the Fuchsian group defined by H1 of these Mobius map G and F. Okay, and you can take the quotient space of the hyperbolic plane by the Fuchsian group gamma, and the quotient space is a complete Riemann surface topological equivalent to the Lochness monster. So this is the construction, an easy construction to get a Fuchsian group uniformizing to the Lochness monster. Now, I'm going to generalize this construction. So the first step to generalize this construction consists to take a phi tuple of the 5-dimensional real space. Okay, the tuple is A0, B0, C0, D0, E0. Okay, show that this tuple satisfies the relation, this relation. Okay, you need that this guy satisfies this relation. So you draw this point over the real axis. Okay, see the real axis. You draw over the real axis this point. Now we draw a special half circle. The first one, half circle, is rho 0. This guy has ends point A0 and B0. The second one, special half circle, is sigma 0 is the first one. The second one is rho 0, having ends point B0 and C0. The next half circle is hat sigma 0, having ends point C0 and D0. And the last one is the half circle hat rho 0, having ends point D0 and E0. Now, in a way, you can label like a colors, okay? Rho 0 and hat rho 0, you draw it with a red, and the other half circle with a blue. Now you can identify circle having the same color with a Mobius map. Okay, you can identify sigma 0 and hat sigma 0 with a Mobius map F0. Okay, and in the same way appear the Mobius map G0, identify the half circle rho 0 and hat rho 0. Okay, remember, when you take the generate group by F and G, okay, and take the quotient space given by this group and the hyperbolic plane, you have a surface topological equivalent to the torus minus ADX. Okay, this is the first step. Okay. Okay, now the second step is, okay, you take your first 5 tuple and put my 5 tuple, put together, but put together suitable. Okay, so now for each n in the integer number, you take a 5 tuple, right? Its tuple is an, bn, cn, dn, en of the 5-dimensional real space, so that this guy satisfies this condition and satisfies that the en negative 1 is equal to an. You need this other condition, right? When you take your 5 tuple, and again, you draw a strip from this a 5 tuple, okay? So you define your first 5 tuples, sorry, and draw the strip having ends point an and en, right? So over there, you develop or you draw the 5 circles over there with the respective Mobius mass, so that this Mobius mass identify half circle by pairs, okay, in each one of these strip, okay? So in this way, you need to take the set conforming by all these Mobius mass defining each one of these strip. And define the Fuchsian group generated by this Mobius map. So in this way, you can prove that the quotient space given by this Fuchsian group, the quotient space given by the hyperbolic plane under the Fuchsian group gamma is a complete surface topological equivalent to the Lossness monster. So to end the presentation, we introduce the following problem. We want to determine the parabolicity of this lossless monster given by the theorem before. Okay, it's all, guys. Thank you very much.